Hi everyone, this video is supplementary for the lecture 1. One student asked me about the more detailed information for the part 5. Note that the presentation material is beyond the scope of this lecture and it is optional to watch this video. In order to calculate the band structure, we have to solve the Schrödinger equation. For the Hamiltonian operator, which is the sum of the kinetic energy and the potential energy, eigenvalues are found. They are eigenenergies. In a 1D case, the kinetic energy can be written as the second derivative of the wave function. Let's test our free electron wave function e to the ikx. We can immediately prove that it satisfies the Schrödinger equation with E equal to half square k square divided by 2m. Now we introduce a periodic potential. By considering only the cosine term, we have the following potential. Let's test our free electron wave function e to the ikx again. Then, in this time, Hamiltonian applied to e to the ikx is other terms which are not proportional to e to the ikx. Therefore, the free electron wave function cannot be a solution under a periodic potential. At the boundary of the Brillouin zone, k equal to pi over a, we can notice that exponential I pi over ax is exponential I pi over ax and exponential minus I pi over ax. At k equal to minus pi over a, we have a similar relation. In this sense, exponential I pi over ax and exponential minus I pi over ax are coupled. Although each of them cannot be a solution of the Schrödinger equation, a linear combination of them has a chance. Let's try. The coefficients are denoted C plus and C minus. After applying the Hamiltonian operator, we have the following result, and it should be proportional to the original function. Collect the coefficient of exponential I pi over ax, then we have a simple relation. The coefficient of exponential minus I pi over ax gives another relation. We can easily rewrite two relations in a matrix form. Consider a vector whose entries are C plus and C minus. Then we have the following eigen problem. In the part 5 of the lecture 1, a normalized version was shown. I hope that this video can be a sufficient answer to the question. Thank you.